This is ECE 343, Signals and Systems, fifth part of Chapter 3. Last time we took a look at discrete-time convolution, and we looked at two different methods for computing the discrete-time convolution sum. The first method that we took a look at was a direct evaluation method, while the second method was the three-step method that was very similar to the three-step method that we employed for the convolution integral back in Chapter 2. Today, in this lecture, we're going to look at two additional mechanisms for carrying out the convolution sum. The first one is something called the sliding tape method, something that is covered in the book, so you can get additional details there if you like. The second one is not covered in the book, and it's something I will call quick convolution. Once we've covered these two additional methods for computing the convolution sum, we'll go ahead and take a look at the topic of stability, both from an internal and external perspective, and we'll make some final comments to wrap up Chapter 3. The sliding tape method is really just a graphical vector version of the three-step method we've already looked at. Rather than go back through all those steps in an explicit way, I'd like to demonstrate the sliding tape method through a simple example. So let's go ahead and take a look at an example of two signals that we want to convolve together. I have a signal x of n depicted here. It's a 4-length signal. I've gone ahead and shown a vector depiction of it. It goes 1, 2, -2, 3, with the -2 element being located at n equaling 0. We want to convolve that signal xn with the signal hn, which I've shown. This is a 5-length signal that goes through the elements -3, 1, 0, 1, 2, with the leftmost 1 being where the n equaling 0 point is. If I was going to solve this with the three-step method, the very first part of that would be to go ahead and plot x of k and h of n minus k as functions of k. I'm going to do a version of that, but rather than using a physical graph, I'm going to just plot out the elements of these vectors on a tape, and we'll go ahead and see how that works out. In the first case, we had an xn vector, and I want to make that an xk vector, again, drawn out in that vector sense, just along this tape that I've already drawn in there. This is a direct translation, so it's going to look exactly the same. The first non-zero element is 1, and then I'm going to get a 2, and a -2, and a 3, and we know everything after that is 0, so I'll go ahead and plug in a 0. So this tape, right, this little tape that I have drawn off on the right, is a graphical depiction, vector style, if you will, of that signal x of k. Each different box is for a different value of k. We knew that the -2 element, right, was when the argument was 0, so that is our k equaling 0 element. So I'm going to go ahead and put k equaling 0 there. And it just turns out it will be convenient for us to go ahead and know what the value of k is for the leftmost element. So I can see the leftmost element is two blocks or 2 spaces away. So it should be k equaling -2 for that element 1, which is the leftmost element of my x of k tape, my x of k vector. The next one I need to do is my h of n minus k as a function of k again. So this is a flip and shifted version. In order to flip it, right, I just take my original vector and I write out the elements in reverse order. The original order for h of n was -3, 1, 0, 1, 2, right? Now I just need to go them in reverse order. So I'm going to start out with the 2, then I'm going to have a 1, 0, 1, and -3. Again, we need to notate where these boxes are. We knew that the leftmost one was at the argument equaling to 0. Now we're going to have the rightmost one at the argument 0, right? That's just the flip. And then we shift that by n. So here, this value 1 that's rightmost is going to be k equaling n. And again, it's probably most convenient in this particular case to look at what is the rightmost element in this case, what its position is. And so we know that that guy just being 1 to the right of the k equaling n element, that's going to be k equaling n plus 1, something along those lines. I've gotten basically then an equivalent to step 1 of the three-step method, just using a vector or tape representation of my signals. Now I need to go ahead and let these two tapes interact with one another. I've gone ahead and copied those tapes down already. And what I know is that h of n minus k, right, moves as n changes value. So I'm going to go ahead and grab that tape. We know that that tape right there, the h of n minus k, right, as I choose different values of n, this tape moves relative to the other tape. The first tape was x of k. The one below that is moving right now is h of n minus k. We've already seen this. We just did it with graphs rather than with vector notations with these tapes. As long as there's no overlap in these guys, something like this, right? We know that there's going to be a product of x of k, h of n minus k just being all zeros. And if you sum up a bunch of zeros, you get zeros. How long does that happen? We can look at that happening just to the point where that element, the rightmost element of h of n minus k, right, is just to the left of the leftmost element of x of k. That occurs when n plus 1 is less than minus 2. So I'm going to go ahead and drop this guy down there, and we'll go ahead and start drawing out some of these things in here. So we know for n plus 1 less than minus 2, or n less than minus 3, I'm going to get a sum of 0 being equal to 0. So we already know that one. That's 1. And usually in the sliding tape method, you are going to have some zeros off on one side or both sides of the final result. And maybe you don't even need to worry too much about writing those explicitly down. It's the non-zero values that are going to be the most interest. Okay, so what's the first non-zero value? These are going to be some different values of n. And let me just clean this up a little bit. I'm going to create a little table here. And this table is going to be my output, right? The convolution, which I'll call y here, for different values of n. So I'm going to look at different values of n and look at y, and let's just make sure that we explicitly say it, y equals x convolved with h. We already saw for n less than, right, minus 3, we got 0, something along those lines. And now we're going to look for some different values. We're going to look at like minus 3, we'll look at minus 2, we'll look at minus 1 and 0 and 1 and 2 and 3 and 4 and 5 and so forth, something like that. We're going to look at all these different values and see if we can compute out what is the corresponding values of y. In this sliding tape method, our regions are each going to be 1 unit in size because we're going to just do a direct inspection of the overlap, do the products and sums, and then write down the value. So let me go ahead and grab this moving tape, right? This is the h of n minus k, and let's move it to that first value when n equals minus 3. When n equals minus 3, n plus 1, minus 3 plus 1 is minus 2, and that's when these two tapes overlap by 1 element, okay? So what is the product now of h of k times x of k times h of n minus k? Well, what we can see here is we get 1 times minus 3, right? That's one value, and everything else is 0. So I'm going to get 1 times minus 3, that's just going to be minus 3, plus a bunch of zeros. So I'm going to get a minus 3 here for my value of y in that particular case, because there was only one overlap piece. So I get minus 3 in there. I'm going to now slide over, right? So that's it's called the sliding tape method. I'm going to slide over 1 unit, right? And so now we're going to have what? We're going to have an overlap of 2 elements in these tapes. I'm going to have 2 overlapping with minus 3 and 1 overlapping with 1. If I multiply the corresponding elements, right, I get 2 times minus 3, that's minus 6, plus 1 times 1. So minus 6 plus 1 is minus 5. So for this next one over, I should get a minus 5 value out, something along those lines. I'm going to go ahead and slide again then. I'm going to go ahead and grab this guy and move it. And you can do this the same way on your own piece of paper. You can go ahead and make tapes actually on physical pieces of paper and cut them out so that you can slide them one against the other. It really helps in the visualization. So one more over, right? This is when n plus 1 equals 0, or n equaling minus 1. That's the next slot we're working on. What's the overlap? Minus 2 overlaps with minus 3, 2 overlaps with 1, and 1 overlaps with 0. And all the other overlaps are 0. So I'm going to get 2 negative times minus 3, that's 6. And then I'm going to add to that 2 times 1. So 6 plus 2 is 8. Plus 1 times 0 is just 0. So I should get 8 for this next value. So minus 3 times minus 2, 6, plus 2 times 1, that's 2 more. That's going to be 8, plus 0. So I should get 8 in here. I'm ready to move on to the next value. You probably are getting a pretty good idea of what this is looking like now, right? Moving over one more time, and now I've got an overlap in this particular case that is going to be showing something that we have that element minus 3 overlapping with 3, minus 2 overlapping with 1, 2 overlaps with 0, and 1 overlaps with 1. So if again I go through and I multiply corresponding points, I'm going to get, working from left to right, 1 plus 0 minus 2 minus 9. So that should be 1 minus 2 is minus 1, minus 9 is going to get minus 10. So I should be able to get a value of minus 10 at n equaling 0. Going to keep going over here. One disadvantage of this method that you can see right now is that you got to physically do this for every possible overlap location. So it is a little slow, but it is pretty simple, something like that. So I'm going to move it one more over. Overlap in this case, what do we get? I'm not even going to bother spending too much time here. I'm going to get 1 times 2 plus 1 times 2, that's 4, plus 0 plus 3 is 7. So the next one over here should be a value of 7. Going to go over again, right? I'm going to go over one more on this guy. And so I'm going to take this whole sliding tape again that was H, move it one more unit over to the right. Now the overlap looks like what? 2 times 2, that's 4, minus 2, right? So 4 minus 2 is 2. So I should have a value of 2 in there. So I got a value of 2 at y, for y for n equaling 2. Go another step over. I'm going to grab that sliding tape and let it continue its journey, right? So I'm going to go over one more step, right? Something along this lines. Now what do I get? I get minus 2 times 2, that's minus 4, plus 3, that's going to be a minus 1. So my next value is minus 1. I'm going to slide over another one here, and now we're getting pretty close to the end, right? As I move one more over here, I get 3 overlapping with 2. That is 6. Everything else is something times 0. So I'm just going to get a bunch of zeros added into that 6. That just gives me 6. And then for any value further than this, right, as I go to this place and further to the right, I should be getting an overlap of nothing. There's no overlap between these two waveforms. The product is going to be 0 everywhere, and I sum that 0 up. I should just get 0. Let's figure out and just make sure that we do recognize what values of n that corresponds to. If I go ahead and look at my sliding tape, h of n minus k, the rightmost element was n plus 1, right? So if I move to the left of that, the next one over would be n, then I would be at n minus 1, n minus 2. So this guy is n minus 3, the leftmost one. When n minus 3, right, lines up with that 0 or greater. So if I look at the x of k, the minus 2 was at k equaling 0, the next one was k equaling 1, and the next one was k equaling 2. So when n minus 3 is equal to 2 or greater, so that means n being greater than or equal to 5. So if I have greater than or equal to 5, I have no overlap and I get 0. I finished my result, the final answer in this particular case, right? I could do it in a traditional vector style. I could just say y is equal to minus 3, minus 5, 8, minus 10, 7, 2, minus 1, 6, something like that. And then just to be complete in that vector notation, let's go ahead and identify the n equaling 0 element, something along those lines. Okay, so that was pretty easy, pretty straightforward. The sliding tape method is a relatively simple way to carry out these convolution sums, particularly if you have finite duration signals that you are convolving. One little final check I might just do here for fun is a reminder of some properties that we looked at last time. This x of n is what? It is a 4-length vector, right? So we can see in this particular case that the length of x equals 4. And then if I look at h, that's a 5-length vector, right? So L sub h equals 5. And I know through the width property, which you could also express as the length property, that the length of y, right, is Lx plus LH minus 1. That was one we derived before. So 4 plus 5 is 8 minus 1 is, or 9. 4 plus 5 is 9 minus 1 is 8. So I should have a length 8 result. Let's see if that worked out. If I count in here the number of non-zero elements that I have, right, starts over here at minus 3, right? That's the first one. Second, third, fourth, fifth, 6th, 7th, 8th. Sure enough, I have a vector who has 8 non-zero elements. So that width property or the length property can be used as a quick check just to make sure that things are lining up. So that was one of the two methods. One that should seem pretty familiar. It's just a little bit of a twist on something we've seen before. That 3-step method, we aren't so rigid about computing out generic, right, generic regions in the way that maybe we would normally do with the 3-step method. We aren't really parameterizing the waveform. We're just taking tapes with numbers, overlapping them, and then doing corresponding points being multiplied and then added together. Really pretty straightforward. Works well, again, as long as the overall things that we are convolving are finite duration. Quick convolution is a different technique that uses a familiar multiplication technique to convolve signals. This is one that I kind of like because later on when we go to the transform domain, we're going to see that convolution does become multiplication. And while the reasons aren't exactly the same here, it's kind of our start to see this interaction between convolution and multiplication. This is very much like the direct method if you go back to that first method we talked about, evaluating convolution, but it's in a very kind of sort of a unique way of carrying out that direct method. And it is again a case where it's best if the signals are finite duration. So if you have signals that are infinite in duration, right, you might find out that neither the sliding tape nor the quick convolution method works particularly well. Let's return to the same example we just did because we already know the answer. And let's go ahead and carry this particular operation out using this idea of quick convolution. Again, I'm not going to write out the rules. I'm just going to show it through this particular example. This is going to be something that we can carry out this convolution using operations that are very similar to long multiplication that you learned back in grade school. So I'm going to go ahead and grab one of my two signals. I'm going to grab H first. I'm going to go ahead and write out its elements. So -3, 1, 0, 1, 2. And I would like to multiply that guy by the other signal, 1, 2, -2, 3. So I would normally just put that one below. So I have a 1, 2, -2, 3. One little thing that I'm going to do here is I'm going to use a radix point or a decimal point to help me identify where the n equals 0 point is on each of these two waveforms. So I'm going to use a decimal point, and I'm going to put that decimal point to the right of the element that is the n equaling 0 element. So in H, we can see that the n equaling 0 element is the first one. So I'm going to just go ahead and put my decimal point. That's kind of my placeholder here, right? Just to the right of that first one. The second signal, my x of n, right? We could see the n equaling 0 element was the -2. So I can go ahead and just put my decimal point there to the right of -2, something along those lines. And now what would I like to do? I'd like to go ahead and do long multiplication of these signals. What's the rule here? I take the lower argument, right, the 1, 2, -2, 3, and I take its rightmost element, 3, and I multiply it by each of the elements above, right? And I just try to follow those terms along. So 3 times 2 is 6, right? Next one is 3 times 1 is 3. 3 times 0 is 0. 3 times 1 is 3. 3 times -3 is -9. Next line down, I'm going to take the -2 element times all that stuff, right? But I need to shift everything over by 1. So I'm going to feed in a 0, and then I'm going to take -2 times 2 is -4, -2 times 1 is -2, -2 times 0 is 0, -2 times 1 is -2, and -2 times -3 is 6. Going to go to the next line, shift in 2 zeros, right? 2 times 2 is 4, 2 times 1 is 2, right? 2 times 0 is 0, 2 times 1 is 2, and then I'm going to have 2 times -3 is -6. What you'll see here is that whatever I'm using on the bottom, right, those are my scale factors for shifted versions of the thing on the top. Now, I gave the top here as being my h's, right? So my x's here, these are my x's down on the bottom that I put in here. My h's are up here, right? When I do this multiplication, right, this first line looks like h multiplied by that rightmost value of x. The next one down is h multiplied by the second rightmost value of x, and so forth. So every single one of these lines looks like a scaled value of h just shifted 1 unit relative to the other. This is exactly what the direct method does. We have one more step in this particular case. I've done the first 3. I have one more to do, so I'm going to feed in 3 more zeros, right? And then I'm going to have 1 times that guy. So I'm going to have 1 times 2 is 2, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, and 1 times -3 is -3. And now I'm just going to add these guys up together. The addition here needs one little modification. So up to this point, we've used multiplication rules just like normal, basically. But the last little tweak that we're going to do is that when we add up all these columns, we're not going to do any carrying. We're just going to add them all up and give a number that could be greater than a single digit, right? So 6 plus a bunch of zeros is 6. 3 and -4 is -1. 4 and -2 is 2. 3, 2, and 2 is 7. -9 minus 2 is -11, plus 1 is -10, and I'm going to leave it as -10. I'm not going to carry, right? 6 and 2 is 8. -6 and 1 is -5, and -3 just gives me -3. Now take a look at that sequence. -3, -5, 8, -10, 7, 2, -1, 6, and compare it to what I had previously. Same exact thing. If you take a look at that guy, -3, -8, -3, -5, 8, -10, 7, 2, -1, 6. These guys are identical. So this thing matches. It matches what we did before. We know that it's carrying out this convolution correctly. So I am getting a representation for y of n. This whole thing is my y of n. The only thing I'm missing at this point is where is that n equaling 0 point? Well, how would we do this in regular long division? We take a look at how many digits, right, are to the right of those decimal points. So I have what, 1, 2, 3, and 4, right? So there's 4 digits over there that were to the right of decimal points, right, or those radix points. And so my final result should have its decimal point a total of 4 from the right. So I could come over here, 1, 2, 3, 4, and I'm going to put my decimal point. And what is that decimal point's meaning? It is just to the right of the n equaling 0. So if I come in here and identify just to the left of that guy, n equaling 0, I should be done. Again, we can go back and look at what we had before, and sure enough, right, minus 10 was n equaling 0's element. So we have an exact answer that matches our three-step method that we just did through the sliding tape method. Very quick, especially because almost everyone has a lot of practice doing a long multiplication like this. So it employs skills that you've learned before in a unique or a new way to carry out the operation that you want. Really nice. Let's do one final convolution example. There's a couple of reasons I'd like to do this. Let's just do it as a final convolution example. So I'm going to go ahead and look at a lot of this I've already pre-written. We're going to go ahead and find the zero state response, right, for a system that's described by the constant coefficient linear difference equation given here. Y of n plus 1 minus a half yn is equal to x of n plus 1. This is a first order system, right? If you look at the output terms y, right, this is an advanced form of that difference equation, and we see the highest advance there is 1. So it's a first order system. And I'm going to be looking at the zero state. So that means all the initial conditions are 0. There's no energy initially in the system. And it's going to get an output purely by the driving function, which I'm taking in this case as being xn equaling a half to the n u of n. We've already known, because we derived this before, right, that the zero state response, y zero state response, should be equal to x convolved with h. That's how we get the zero state response. We need that convolution operation. So for me to be able to solve this, to find the zero state response given an input that is a half n to the half n u of n, I'm going to need to be able to get that unit impulse response for this particular difference equation. So this will be a quick reminder of that process of finding the unit step. We looked at that 2 lectures ago, I believe. So in order for me to do that, the first thing I'm going to do is I'm going to take a look at the characteristic equation. In this particular case, the characteristic equation is going to be gamma minus a half, set it equal to 0, right? Solve for the root. That's a single root. It was a first order system, no surprise. I get gamma equaling to a half. I go ahead and go back to my general form for the unit impulse response closed form solution. It could potentially have a delta function. But the bn by an coefficient that precedes the delta here, because bn is equal to 0, there's going to be no delta function. So I'm going to get 0 delta n, and then I'm going to have something that looks like that zero input response. That's just a scale of that natural mode, 1/2 to the n, first order system, just one mode. So I'm going to get a c 1/2 to the n u of n. I would like to be able to find that value c in order to get the complete final form of this h of n. And so I'm going to have to recurse a value of h of n so that I can find that unknown coefficient c. I can get that recursion by doing what? I go back to my original difference equation. I'm going to let x be a delta function, and I know when I make x a delta, out pops h. If I delay that equation after I've made that substitution, delta for x and h for y, and then solve for h of n, I end up getting this expression here. H of n equals a half hn minus 1 plus delta n. And I just need one value here, so I'm going to recurse a single value, h of 0. What is h of 0? It's a half h of minus 1 because the system is causal. That's just a value of 0. And I'm going to get delta 0, which we know delta 0 is the only place the delta function is non-zero, right? So that's when we get the 1. That whole thing comes to a 1. What does that have to be equal to? It has to be equal to this closed form expression, right, evaluated at n equaling 0. So if I go ahead and put n equaling 0, then I'm going to get c 1/2 to the 0, that's just 1, times u of 0, which is also 1. So I'm going to get c times 1 being equal to 1, or c equaling 1. So I've gone ahead and recursed the value, right? That was h of 0 being equal to 1. Use that when comparing it back to the closed form solution to create a system of equations in the number of unknowns. There was only one, so only one equation, and solve for the unknown, c in this case. That gives me this final representation for the unit impulse response. I didn't have to give this. I just wanted to make one more example of getting this h of n from a difference equation. So what I see here is h of n equals a half n u of n. And oh, that just happened to match the input that I was putting in there. So I'm driving the system at a natural mode. That's something we've talked about before in the context of continuous time systems. We're expecting something like resonance to come out of this. Let's go ahead and see if the convolution confirms that or verifies that. So to get the zero state response, right, what do? I just take h convolved with x. H and x both have the same form, both of them. If I was going to draw it out really, really short, right, we would have values that would be cutting down by a half, starting at 0, and it would be 0 beforehand. So this is both x and h. They're causal exponentials. Take one of those guys, flip and shift it, right? You're going to get the causal exponential or an anti-causal exponential, one that points in the opposite direction, something like that. And you're going to look at the interaction between these two. When n is less than 0, that's the first region. We had done an example very similar to this earlier. When n is less than 0, there's no overlap. That means I'm summing up a bunch of zeros and I just get 0. For n greater than or equal to 0, that's the second region. This particular convolution only has 2 regions. I'm going to get the overlap part as going from 0 to n, right? If I did the flip and shift versions, if I looked at this guy, for example, as being maybe x of k, right? K equaling 0 is the first non-zero value. This guy here would be my h of n minus k. So you flip it, that made it go leftwards, and then shift it by n. This is k equaling n is the lead edge of that. When n equals 0, we start, right? And what's the overlap? It's going to be dictated on the left by the leftmost part of x, and it's going to be dictated on the right by the rightmost part of h of n minus k. So my sum limits here, right, are going to go from 0 to n. From 0 to n. And what are we going to get in here? We're going to get a product of these two functions. X of k over that region is just 1/2 to the k, right? We had seen that before. It was 1/2 to the n, u of n, right? So we replaced n with k when we made it x of k rather than x of n. H of n minus k is just going to be that half raised to the argument, now n minus k. So we're going to get a half n minus k. So I have to be able to handle this sum going from 0 to n of 1/2 k times 1/2 to the n minus k. Well, there's two terms here. They both have the same base, different exponents. I should just be able to add the exponents. So 1/2 to the k times 1/2 to the n minus k is the same as 1/2 to the k plus n minus k. The k and minus k cancel, and I'm left with just a half to the n. So an equivalent version at this point is my y of n, right? It's just going to be a sum from 0 to n of 1/2 to the n. I'd like to go ahead and evaluate this sum. On first blush, and when I give examples like this, similar examples to this in my typical lectures, I oftentimes see people immediately go to the geometric sum formula and start cranking out on the geometric sum. I'm just going to point out that the geometric sum, right, involves something like, if we look at a geometric sum, right, it looks something like this, a summation on k going from some a to b of r to the k, right? So we have some value, that's r, raised to the some variable k going from limits a to b. Almost all of that looks right here except for that raised to the power. I'm not raising here to the k, I'm raising to the n. That is a constant with respect to the some variable. So that whole term, 1/2 to the n, can be pulled out front. 1/2 to the n, and then I'm going to be summing what? K equaling 0 to n of 1. How many terms are in this sum? 0 is a placeholder, right? So 0, 1, 2, 3, all the way out to n, there's a total of n plus 1 terms. Each of them has a value 1. If I add 1, n plus 1 times over, right, I'm going to get just n plus 1. So I can do that one just by visual, right? There's n plus 1 ones, and if you add them all together, I should get n plus 1. So now I'm getting somewhere. I should be able to just come up with this output, y of n, right? At least this is for n greater than or equal to 0. It's going to be a 1/2 to the n times n plus 1. Now, if I wanted to incorporate the initial conditions in just an easy way, I know that it's that for n greater than or equal to 0. It's 0 before that. I can achieve those regions by just multiplying this whole thing by u of n. Now I have a single expression. It's still piecewise constructed, right? But that fully reflects both region 1 and region 2. What would I like to point out here? We were able to do the convolution. We did it with a three-step method. But notice what we did. We had an input that exactly matched a natural mode of the system. The natural mode was 1/2 to the n. That driving a system at a natural mode is like repeating that root, right? What happens when we repeat a root? What happens when we get resonance? New modes occur. When we repeat a root, what is the extra modes that come out of that? They're things like n times that mode or n squared times that mode. And what do we see here? We see an n times that mode. We had the original 1 times that mode, right, that we'd expect, but we get a new mode, n times 1/2 to the n. That's because of the resonance. That's because I'm driving the system at a natural mode. Nice kind of pulling together of a lot of topics that we've seen throughout chapter 3. Okay, time to change gears now. We're going to be rapidly going through this next set of topics. These other topics follow very, very similar to what we had seen before in chapter 2 with continuous time systems described by constant coefficient linear differential equations. We're just going to be looking at it for these cases of discrete time systems described by constant coefficient linear difference equations. We can easily assess stability, both internal and external, from constant coefficient linear difference equations. Let's start with asymptotic, or what is also internal stability. So we're going to go ahead and look at this case of asymptotic stability. Asymptotic stability basically says if you stuff energy into the system, right, does the system respond by letting that energy bleed away in a nice controlled way, or does that energy come out, ever growing in such a way that it wants to blow up, destroy the universe kind of behavior? That would be unstable. Well, what is it that we get for an output from a system when we stuff energy into the system? That's just the zero input response. And we know the zero input response is completely comprised of natural modes, which, as long as we didn't have repeated roots, that's the case we'll look at here, looks something like a gamma to the n. I could put that in a polar form, norm of gamma raised to the n, e to the j theta n, where theta is the angle of my potentially complex number gamma. How does gamma to the n decay to 0? That's stable behavior as n goes off to 0. Well, it decays as long as the magnitude of gamma, right, raised to the n, also goes to 0 as n goes to 0. This first part, right, is the envelope to that gamma to the n. The second part, right, the e to the j theta n, is just something about a rotation or an oscillation. We've seen that before. That doesn't help it decay or grow, either one. That just causes it to oscillate. So for us to get stable behavior, something that converges, something that bleeds energy down to 0, really requires that the magnitude of gamma, right, be less than 1. Because if you have a number less than 1 raised to n as n goes out to infinity, that term goes to 0. That's stable behavior. So we get really simple kinds of tests here. Asymptotic stability, okay, a system is asymptotically stable if the characteristic roots are completely contained within the unit circle for all characteristic roots. If you remember continuous time, what did we check? For asymptotic stability, we just said all the characteristic roots were in the left half plane. So our boundary there was looking left half plane, right half plane. For discrete time, we need to look at a boundary that involves the unit circle. So asymptotic stability says, are all your roots inside the unit circle? Marginal stability is you can have some roots that are inside the unit circle, and you can have potentially non-repeated cases, right, where they are on the unit circle. This is very similar to having non-repeated roots on the imaginary axis for continuous time. We knew that that imaginary axis was the boundary for stability. The unit circle for discrete time case is the boundary for stability. And if we have non-repeated roots on that boundary, then we would have modes, right, that are neither growing nor decaying. That's just on the edge of stability. Instability or an unstable system is one where you have a characteristic root that is outside the unit circle, or perhaps you have some repeated root on the unit circle. So simple tests. It's the same sort of logic. For continuous time, we had asymptotically stable for everything in the left half plane. Marginally, you could have unrepeated roots on the omega axis. Unstable was repeated roots on the omega axis or a right half plane pole. Here, for discrete time, it's exactly the same idea, except for instead of looking at the imaginary axis, we're looking at the unit circle. So all your poles inside the unit circle, asymptotically stable, up to and including non-repeated roots on the unit circle. Now you have marginally stable. Unstable is having any root outside the unit circle or having repeated roots on the unit circle. Some very quick examples then. Let's look at 4 different cases. In this first case, I'm just going to show the characteristic polynomials. I'm showing them in factored form. The first case corresponds to a signal or a system with 2 roots, so it's a second order system. And I see in this excuse me, particular case that we have roots, right? Gamma 1 being equal to a half and gamma 2 being equal to minus a half. Both of those guys, norm gamma I is less than 0 for I equaling 1 and 2. What does that tell me about this guy? It is stable. This is an asymptotically stable system. So we'll go ahead and do that in green. Go to the next one over and I take a look at that guy. I have gamma 1 equaling 2, gamma 2 equaling minus 2. Both of those are outside the unit circle, so norm gamma I, right? Norm gamma I in this particular case is greater than, it is greater than 0. Greater than 1. I don't know where that 0 came from. Thinking back continuous time. Let's correct that. We're looking at the unit circle. So gamma I is greater than 1, right? So outside the unit circle for both I equaling 1 and 2. So what does that mean in this case? This is an unstable, asymptotically unstable case because they are outside the unit circle. If I was going to go ahead and take a look at that guy, right, go ahead and draw your plane, go ahead and draw the unit circle and show where those roots are. One's at 2 and one's at minus 2, right? Both of those outside the unit circle. If I go to the first case, right, I could have looked at this guy in here, put the unit circle for reference. I would have found 1 at a half and 1 at minus a half. Both of those guys inside the unit circle, so a stable case. The next one down is a first order system, right? Single root at gamma equaling 1. So I can see in the space, gamma equaling 1 is my root. If I went ahead and I drew out the location of that guy, I'm going to go ahead and draw that thing. And I'm going to draw my unit circle in there. Gamma equaling 1 is just right there on the unit circle. So this is going to have neither growing nor decaying behavior, right? This is going to be something that has a constant envelope. It doesn't blow up, but it also doesn't decay to 0. It's right on that boundary of stability. So this is going to be marginal stability, marginally stable. Because I neither grow nor decay. Now what happens if I go ahead and I repeat that? So I have gamma 1 equaling gamma 2 equaling 1. Now in this particular case, I'm looking at, again, I could look at where those guys are. I could go ahead and draw my unit circle out there. Not only do I have 1 at 1, but it's repeated. So I'm going to show that twice over. What does that mean? I'm going to have a mode like 1 to the n, right? That's the unrepeated case. 1 to the n, if you look back here, my gamma on the case number 3, it's like a 1 to the n. That's just 1, right? That's like a DC value. Neither grows nor decays. If I come over here to this case number 4, where I've got gamma 1 equaling gamma 2 equaling 1, I'm going to have gamma 1 to the n. That's like a 1 to the n. But I'm also going to have an n 1 to the n, which is like an n. That guy grows, right? This one here grows. And that kills this thing as far as stability. So this is also unstable. I have a repeated root on the unit circle. So just a few cases. Assessing stability, very simple. Take a look at where your characteristic roots are in the complex plane. If all of them are inside the unit circle, it's stable. If there's anything outside of the unit circle, it's unstable. If you have some roots that are on the unit circle but not repeated, you would have a marginally stable system. Anything that gets repeated on the unit circle would cause it to go unstable. We can also look at BIBO stability from an external, or stability from an external standpoint. This is BIBO, bounded input, bounded output stability. We saw this again back in chapter 2 with continuous time systems, and it goes something like this. We're given that the input is bounded. What do we mean by a bounded input? That means that the magnitude of x has some maximum largest value, mx, which is a finite number. So the magnitude of xn is less than or equal to some finite value mx. Given that, can we guarantee, can we say that the output magnitude is also bounded by a finite number? If we can, then it is BIBO stable. If we can't, then it is not BIBO stable. So this is something about determining or trying to look at stability purely from an external standpoint. We're only looking at this by applying an input. We aren't really getting to see what's going on inside the system. Well, what do we know about y then, the output of the system? We can get the output of the system through the convolution integral. I've gone ahead and drawn that where I flip and shift x instead of h. If I want the magnitude of y, right, I just take the magnitude of that convolution sum. So magnitude of yn is the magnitude of the sum on k, going minus infinity to infinity, h of k, x of n minus k. A magnitude of a sum is always less than or equal to the magnitudes, or the sum of the magnitudes. That's a triangle inequality. Same game that we played back in chapter 2. So I know this whole thing is less than or equal to the sum of the magnitude of a product. It's just a product of the magnitude. So I'm going to get magnitude h times magnitude x of n minus k. But what do I know? I know from my if, my given, right? I know that x is always smaller than a finite value. So this guy is always less than or equal to some value mx. And I'm just going to pull that mx now outside the sum sign. For this guy to be less than, if I want to know, is this thing less than infinity? This is a finite number, right? Divide both sides by a finite number, and we can get to this, right? Is the impulse response function h of n absolutely summable? If it is, we can guarantee that the norm on yn is also bounded by a finite number. So our test is simple, and it's exactly the same as we saw, at least in spirit, to how we assessed internal or external stability for continuous time systems. When we looked at BIBO stability for a continuous time system, we said, is the unit impulse response absolutely integrable? Here we're looking at whether the unit impulse response is absolutely summable. Discrete time systems can't handle integration. They replace integration with sums. That's one way of thinking about it. So it's just the same test we saw before where integrals have been replaced with sums, same derivation, same everything else. So again, stability now is very easy to test. If I have knowledge of the inside of the system, that means I have the difference equation basically, right? I can just look at characteristic roots. That gives me the strongest statements about stability. However, if I only know the external description, if I only have that unit impulse response, I can still determine things like the external version of stability, BIBO stability, by just checking whether or not that unit impulse response is absolutely summable. If it's absolutely summable, I will have a BIBO stable system. By the way, a system that is marginally stable, that's an internal measure, right, will be BIBO unstable, right? So knowing that something is BIBO unstable is not really a complete measure of stability, right? You could have systems that are unstable in a really bad way. That's like asymptotic instability. You could also have systems that were marginally stable showing up as BIBO unstable. So if you had to choose one version of stability, right, it's usually better to prefer things like the internal description, asymptotic stability, and marginal stability is an extra state for that one. The BIBO or external stability is a little less powerful. In many cases, though, between systems, if they're both controllable and observable, you'll see good agreement between both the internal and external measures of stability. So we have a test then for stability, right? BIBO stability. If h of n is absolutely summable, then the system is BIBO stable. Let's do a very quick example. H of n equaling a unit step. This is a system that functions like a digital integrator, if you want to call it that. So it's a running sum of our input. If I take a look at that impulse response as absolute value, the absolute value of u of n is still just 1 because it's u of n, though it only goes from 0 to infinity. So looking at the absolute value of h summed up over all time is just a sum of 1 from 0 to infinity. Well, that turns out to go out to infinity. That's certainly not less than infinity, so this is not a BIBO stable system, right? This is a BIBO unstable system. It does not have an absolutely summable impulse response. If we looked at a typical system that would come from a difference equation that could give us this impulse response that looks like a u of n, a both observable and controllable system, what we would find is that the characteristic root for this guy would be at 1. It would be a marginally stable system whose root is at 1. And we know that there's an input, right? If 1 is the mode of my system, driving at that mode causes resonance, and that would cause that unbounded output for a bounded input. Last bits from final chapter 3 to end us out in chapter 3. The chapter ends much like chapter 2 ended, talking about some intuitive insights about systems. It talks about resonance, time constants, pulse dispersion, filtering, all this sort of stuff. And they are the same or essentially the same, similar to the continuous time case that we spent quite a bit of time on in chapter 2. There's really no need for me to go back through this. It's something you can easily read yourself. Everything translates essentially the same, okay? So you can have a low-pass system that's discrete time, for example. Its impulse response will be blob-like. If you want to make a quick approximation of that system, you could replace that blob with a rectangle that preserves the peak height, but also the sum, which is like preserving the area. And from that, you can get time constants. And from that time constant, you can get things like rise time, pulse dispersion, filtering characteristics, all that sort of stuff. Read it in the book. It's a pretty quick read. They have some nice examples. Next time, we're going to get to where we've been wanting to probably get to quite a bit. Up to this part in the semester, we've been doing everything through time domain analysis. Now we're ready to go to transform domain analysis. And really, transform domain analysis is where we want to be. It makes things easier. That will start next time.